300,000 tons of steel, one main span of 1,991 meters, 10 years of work across one of the most violent stretches of water in the Pacific. This is how Japan crossed the Akashi Strait. The strait separates Honshū from Awaji Island. Currents here run fast. The seabed lies 60 meters down under soft sediment. Typhoons cross this water every year. Before any steel arrived, surveyors mapped the channel from both shores. They drilled the seabed, measured tides, and tracked wind patterns through every season. The bridge would need to stand against winds of 286 kilometers per hour and earthquakes near magnitude 8. 2 anchor positions were chosen on land. 2 tower positions were marked in open water. From these 4 points, the entire structure would hang. The anchorages came first. On each shore, engineers carved out a deep rectangular pit, walled with interlocking steel sheet piles to hold back the soil. These pits are not foundations for towers. They are the dead weight that will hold the main cables down at each end of the bridge. Each anchorage would eventually contain hundreds of thousands of tons of concrete, locking the cables into the bedrock itself. The work on land was the easier half. Bedrock here is solid and shallow. Excavators cut down through clay and gravel until limestone was exposed at the base. Trucks hauled the spoil away in convoys. Surveyors checked the shape of the pit every day. Once cleared, each excavation was ready to receive its reinforcement cage. But the real challenge was not on land. It was 4 kilometers offshore. Each tower needed its own foundation, set on the seabed in deep water. The solution was a steel caisson, a hollow cylinder 80 meters across, fabricated in a dry dock and towed out to position. 2 of these were built. Once over the marked location, the caissons were carefully flooded and sunk to the seabed in a controlled descent. Divers checked the position. Tugs held them against the current. Then, working from above the waterline, crews began filling the steel walls with a special underwater concrete mix, designed to set without separating in seawater. As the concrete cured, the caisson became part of the seabed itself. Each finished foundation weighs hundreds of thousands of tons. They sit on a prepared bed of crushed stone, 60 meters below the surface. With the caissons in place, the towers could finally begin to rise. Above each caisson, a concrete pedestal was poured to lift the foundation clear of the waves. On top of these pedestals, the first sections of the steel towers were placed. Each tower would eventually rise 283 meters above the sea, taller than most skyscrapers, and built in the open water of an active shipping lane. The towers are not solid columns. They are hollow steel boxes, fabricated in segments at coastal factories and shipped to site. Each segment weighs around 160 tons. They are bolted and welded together piece by piece, lifted into place by climbing cranes that rise with the tower itself. The first sections went up quickly. Workers reached them by boat, then by elevator running inside the growing leg. The pace would slow as the towers climbed, and the wind grew stronger with every meter. By the 3rd year, both towers were halfway to their final height. From the shore, they looked like twin steel skeletons standing in open water. Each leg is a pair of vertical shafts, joined by horizontal struts, designed to twist slightly under wind and earthquake loads without breaking. At this height, weather controls the schedule. A typhoon can shut the site for days. Lifts of new steel only happen when wind speeds drop below safe limits. Inside each tower, internal stairs and an elevator carry workers up. Above them, the climbing cranes inch higher with every completed section. Welders work in enclosed cages, sealed against wind and rain, producing welds that must last 100 years in salt air. The towers are not yet connected to anything. They stand alone. The cables between them are still months away. By the end of the 5th year, both towers had reached their final height. 283 meters above the sea, the top sections were locked into place. The climbing cranes were lifted off by helicopter. Between the 2 towers, a single thin rope was strung from peak to peak, 4 kilometers across. This was the pilot line, the first physical connection across the strait. From it, slightly heavier ropes would be drawn. then heavier still, until a working catwalk could be hung underneath. The towers on their own are useless. They support nothing yet. Everything depends on what comes next. The main cables. 2 of them, each more than a meter thick, made from tens of thousands of thin steel wires drawn back and forth between the anchorages. The next phase would test the limits of what spinning machines could do. Each main cable is 112 centimeters thick. Inside it, more than 36,000 individual steel wires, each thinner than a pencil. They were laid one at a time in a process called aerial spinning. A small wheel ran back and forth along the catwalk, looping a single wire across the strait, around an anchorage drum, and back again. The wheel made the trip thousands of times. As wires accumulated, they were bundled into strands. Then the strands compressed into a single round cable and wrapped in protective wire. 2 cables in total, each capable of carrying the weight of the entire deck, plus traffic, snow, and wind load combined. Then, in January 1995, an earthquake struck Kobe. The towers, still standing alone, moved. When surveyors checked the next day, the main span had grown by almost a meter. The earthquake had moved one tower closer to one shore. Engineers recalculated and continued. The deck was redesigned mid-construction to fit the new geometry. The roadway itself is a steel truss, 2 stories deep and just over 35 meters wide. It was built in sections at coastal yards, then floated out on barges and lifted into place from below, hung from the suspender ropes that dropped down from the main cables. Lifting began at the towers and worked outward toward the center. Each section was bolted and welded to the previous one. The truss design lets wind pass through it rather than push against it, a lesson learned decades earlier from the collapse of older suspension bridges. Section by section, the gap closed. From shore, the line of the road began to take shape across the water. Once the truss was closed, the deck still had to become a road. Asphalt was laid over the steel surface in carefully matched sections, expanding and contracting with temperature without cracking. Drainage channels were cut along the edges. Crash barriers were bolted into place. Lighting poles were installed at regular intervals along both sides. Inside the deck, a separate level carries maintenance access, inspection rails, and service lines. The bridge has its own internal road for crews who keep it running. Wind sensors were mounted at the tower tops and along the main span, feeding data to a control room on shore. Dampers were installed inside the towers to absorb seismic motion. Every joint, every cable wrap, every weld was inspected and logged. 10 years after surveyors first measured the strait, the bridge was structurally complete. The Akashi-Kaikyō Bridge opened to traffic in April 1998. Its main span, 1,991 meters, held the world record for nearly a quarter of a century. The total cost ran close to $5 billion. 2.5 million vehicles use it every year. The bridge has since absorbed several earthquakes and dozens of typhoons without structural damage. The cables are inspected continuously. The towers are still monitored for movement, measured in millimeters. From shore, it looks light, almost delicate, but every meter of it was placed against the current, the wind, and the seabed. 300,000 tons of steel, 1,400,000 cubic meters of concrete, 36,000 wires in each cable, a road that floats above one of the busiest straits in the world and stands.